Well, this might make it exciting. I may actually, oh man, Kang did miss a day. I got to take attendance in this class. What day did he miss? It was last Friday.
Is attendance required for upper level classes?
Taking attendance is required for all my classes. Yes, very exciting. I will begin with a word of prayer before I say anything I have to edit. Dear Heavenly Father, we thank you for this morning, and I thank you for the students, and that we didn't get hurt too badly coming to class. Just help us to glorify you what we do this morning, Lord. In your name I pray. Amen. Yeah, I was worried about slipping around a little bit, but I am, of course, glad we did not cancel because, well, you guys managed to get here, so I guess it was okay. Ooh, so the side ones, sideways next to where? Oh, next to the dorms. Well, this is kind of like those cast a long shadow, right?
Yeah.
So that's the problem. You got no sunlight. All right. So here we go. I'm going to get back to the basics and establish a couple small things that we have been using, but I skipped for the sake of time, which was stupid. I should have taken my time and inserted about a lecture's worth of material earlier, but, you know, here we go. So first of all, this is section 9.4's proposition 13, which is from page 309 of Dummett and Foote. This is known as the Eisenstein. Schoenemann. You probably don't actually pronounce that E, huh? How would you say that? Schoenemann? Or, you have no idea. Well, that makes two of us. Criteria. I'm sure it can be said by people who are not ignorant like me. Not by human vocal cords. It's actually Vulcan. No, I mean, I'm trying to get out of here. Oh, by the way, is my audio bouncing? La 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 la. All right, very good. So this is the, and so apparently, oh, I'm sorry, no, Schoenemann showed this first, and then Eisenstein later. But Eisenstein is a relatively famous individual, so it tends to get credited to him. Let P be a prime ideal. Prime ideal of the integral domain R, all right? And suppose we have f of x equals to x to the n plus a n minus 1, x to the n minus 1, plus dot 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 plus a1x plus a naught, a polynomial with coefficients in this ring, this integral domain R, where n is greater than or equal to 1. Also, suppose that an minus 1, a1, a naught, the coefficients are elements of that prime ideal P. And yet, so you only missed that one Friday, right? Okay, just checking. And the other student who's currently missing, did he miss any class? No, not yet. Okay. And a sub naught is not an element of p squared. What would p squared be? What's that mean? So p squared, just to be clear, it's a set of squared elements of p. So this is like, you know, p squared such that p is in p. That's what that is. Then what's the punchline? Then f of x is irreducible in R of x. Or you could say over R, as we usually do. So the proof is by contradiction. We'll go through it with you guys. And in retrospect, this is a proof I really should have done in 421. because it's not that bad. And yeah, that's also true. So I shy away from it last semester, mostly because when I looked at it in the midst of my class preparation angst, all I saw was statements of divide by and things like this. And if I don't really own it, I will butcher that kind of stuff in class, and it's self-defeating. So I figured just tell you guys to look in the book and read the proof. Professors say, oh, students can read proofs in the book if you ask them to all the time, but you guys got football games to go to, and mates to woo, all kinds of stuff to do. So here, can't forget about the wooing. All right, so proof. I think I'll do it over here so I don't write it so low. Suppose f of x was reducible. So in other words, it's equal to a of x, b of x, with a of x, b of x, non-constant. All right? And r of x. In other words, suppose it could be reduced, right? Notice, so if we look at, say, r mod p, which we can do, right? R mod p of x is a what? We could write that as, technically speaking, that's things like x, that's things like g of x plus the ideal generated by p of x, right? In our current notation. Wait a minute. Yeah. Sorry, I should just say p of x like that, I believe, right? Because p is already an ideal. I don't need to generate it such that g of x is in r of x. Now, But instead of writing that, what Dummett and Foote tends to do is just call this p bar mod p, something like that. Yeah. So with that notation, right? What do we have in terms of the reduction of what's f of x reduced to? So let's consider we have, f of x equal to a of x, b of x. What that implies, now of course I'll do the easy side. You have a of x, b of x, that, right? But what's the left-hand side? If we look at, let me underline it in some other color. What would happen if we say reduce this thing, mod p? So if we reduce this mod p, what happens? We're assuming that an minus 1, a sub 1, can you see me? A sub 1, a sub naught. These are all elements of the prime ideal p, right? So with respect to that notion of modular arithmetic, quote unquote, the residue class is represented just by x to the n, right? So these drop to 0, and we just have x to the n here. And to be annoying, I could put a bar over it, but I just won't. Okay. All right. But what else? But what about r mod p is a what? An integral domain, right? Since what? Since p prime, right? If we take a principal ideal mod a prime ideal, we get an integral domain. And so what's that say? I mean, we could also look at this as A of x bar, B of x bar, right? And if you'll allow me to create other symbols, I don't know. See, it's annoying. I've already used A sub naught here, but suppose I use alpha and beta for the coefficients of these guys. You know, this would be alpha naught plus stuff, alpha to the, I need the letter S, let's say, x to the S bar, right? Times what? Beta naught plus da 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 plus beta to the, I need some other letter, little r, x to the r, right? So if you look at this, you know, this is going to be alpha naught bar, beta naught bar plus stuff, right? In the ring of polynomials with coefficients taken from the quotient of r by p. But we have unique, I mean, we have the usual fun and games. You know, we have coefficients from an integral domain, so we can compare the coefficients of the polynomial on both sides. They have to match. What's the constant coefficient? If you look, you know, on the left-hand side versus the right-hand side, what's the, you know, constant coefficients over here? 0, right? Constant coefficients over here, alpha naught, b naught. So we find 0 bar is equal to alpha naught, beta naught. Now that does not imply that alpha naught and beta naught are 0 in the original ring, but what it does imply is what? That implies that alpha naught and beta naught are elements of P, right? And of course, by the multiplication, the original coefficient a naught of f of x must be the product of alpha naught and b naught. But now a naught is an element of what then? It's an element of something in P times something in P, which is, of course, an element of P squared, which then contradicts the data which we're given, which is that the constant term is not in the prime ideal squared.
Wait, could you go over to the last part? So you're saying that since A naught is a product of elements in P.
Yeah, now that's, and so, no, I'm saying since a naught is by just raw polynomial calculation, it's the product of the constant terms in the reduction.
Right. So,
But,
so you said, and from that we derive that it's a product of elements in P.
right, because alpha naught and beta naught are both in P.
Right.
So a naught, which is again the constant term in the original polynomial,
Right.
is a product of things in P, which means it's in P squared.
But I thought P squared was squares in P, not products of elements in P.
Oh, and so we find the shortcoming of my definition, thank you, P1, P2, such that he doesn't actually define this in this section, so I was speculating. And I see I speculated poorly. Thank you. That was helpful. Is a set. Now, if you had a principal ideal, it really, I think, you know, if you look at the principal, so if we look at, for example, the even integers, right, an ideal of z, then the square of the even integers would be like the ideal generated by 2 squared. So I guess I shouldn't really say it's squares of elements, I think this is the proper definition of it, yeah. I mean, that's what we usually mean by P times P, if we, you know, if this is equal to the product of ideals, P times P, right? I think that's what that would mean. Mm-hmm.
You already have alpha or either alpha 0 or beta 0 belongs to P, not over P, because that's the definition of prime ideal. Either of them?
Well, if either one of them is 0 and not in P, I mean, let's see here. Well, but again, this is the thing is this is an integral domain. So if I have the product of things in an integral domain is 0.
So either of them is 0, not really both of them. I mean, that's
Oh,
the product of the.
you're right. So what? How do I? Huh?
Yeah, because the equivalent O must use some maybe you really have to prove that some I mean like alpha s times beta r where
Well, the thing is, if one of them's in 0, it's also in p. So it's still in p squared.
no p is different from p squared.
Yeah, we didn't show that one of them must be 0. We just
No.
showed one of them.
Here, you're saying they don't have to both be in p. If one of them is 0, it's still something of the form p1, p2. Because 0 is in p squared as well.
Well, but if one of them's 0, then the other one could be anything, because then the result would be in P. Right?
Yeah, but the point is, we're given that the constant coefficient's not in p squared, right? So any which way we play this game, I win, because if they're both in p, we agree it's in p squared. If one of them is 0, 0 is also in p.
Right, but what if one
So
of them
the
is
other-
0? What if one of them is 0 and the other one is not in P? That's possible, right? From our argument so far.
Is that possible? One of them's 0, one of them's not in p.
I mean, obviously it must not be possible because 0.
No, I don't, well, can one of them be 0, one of them? I don't believe that's possible either because,
And when you have two elements not in P, giving you an element in P, which you
No, because 0 is in P, right?
What?
0 is in P.
I know, but then, yes, what I'm saying is that you have two elements multiplied to give you 0,
Right.
which is in P, but it's a prime ideal, which means that if you can multiply to get an element in P, it's an element in P.
there we go.
Wait, I don't follow.
What does it mean for it to be a prime ideal? So suppose, so 0, the point is 0, so 0 bar, how to say this? I think Jonathan's filled the gap. Let me try to walk through it again. So if alpha naught beta naught, right, is, you agree that alpha naught beta naught's an element of P, right?
Yes. So that means either alpha naught or beta naught, by the definition of that.
Right. Oh, so you're saying I could have the alpha naught be 0, and then that doesn't force anything on beta naught?
Right.
Ah, stink. I think he's got a point. Well, I blame Dummett and Foote. This is their argument for page 309-ish. Maybe I'm missing a line, an important line somewhere, yeah? So we're worried about the case that one of them is 0 and the other one's not in P, is that right?
Yeah. Or like one of them, or
Maybe that clearly contradicts the original data that the coefficients are in P. Maybe it's just a calculational observation. Could beta not, just for the sake of, without loss of generality, suppose alpha naught's the 0, and we're trying to show that beta naught's in P, right? How is beta naught appearing? If these multiply out, what do they give us? Alpha naught, beta naught, right? Plus, like alpha 1, beta naught plus beta 1, alpha naught x, and so forth, right? Alpha to the r, beta to the s, x to the r plus s. Yeah. But that's also equal to, of course, x to the n, plus an minus 1, x to the n minus 1, plus a1x plus a naught. So I think we do have things like, for example, we have that alpha 1, beta naught plus beta 1, alpha naught is an element of, well, that minus a sub n minus 1 is an element of P, right? So again, if we know that, what did we were assuming what? What was it we were assuming? We were assuming that alpha naught was 0, and we're trying to show, so we're considering the case.
That's not, I think it was general. I don't think that's.
It's commutative, so without loss of generality, one or the other of them, if they're both in P, we're done.
What is the 0 case equal?
It's an integral domain, so the only way you can get a product of things being 0 is if at least one of them is in.
Right.
Yeah. So considering the case alpha naught.
So alpha naught bar is equal to 0, which just means alpha naught is in P. Right.
Yes, but again, if
we just consider the case alpha naught is equal to 0, that's not fully general.
it's not. Okay, so alpha naught's in P. Great. I'm not going to argue. I think you're right. Yeah. I'm sorry. I forget about what 0. I'm talking about 0. Where am I talking about? My mind. Which 0 am I talking about? Right. I'm thinking of the 0 in the quotient, which is not good. All right. So, which of these things is in P?
Well, we don't even need, we know even more specifically, like we don't even have to say minus a sub n minus 1 is in P. We can just say alpha 1 beta 0 plus beta 1 alpha 0 is in P because the fact of it's going to be 0 in product. Because a sub n minus 1 is already in P.
Yeah.
So then we have does that mean alpha 1 beta 0 is in P?
I believe so.
So therefore either alpha 1 is in P or beta 0 is in P.
But of course, I really want to get that beta 0 is in P, right? So that just pushes the burden up to alpha 1 being in P, right? Logically. So it's still found a way to weasel its way up to the next order. But I think we can repeat this argument, right? Either the... I don't know, guys. There's a...
Well, we have a plus b in P.
Yeah.
That doesn't necessarily mean that a is P.
If we have what?
Like, we have alpha 1 beta 0 plus beta 1 alpha 0 is in P. We know the right term is in P, but does that mean the left term is in P? Like, for instance, if we have P be like the even numbers, and we have 5 plus negative 5 is in P, that doesn't mean either of those. I think I'm forgetting some of the calculation. Like,
Well,
One value is like additive group, so you can subtract and minus and add and form.
yeah, but I'm not talking about. I mean. Oh wait, no. No, we're given.
so I mean, we're given that a sub n minus 1 is in P, so we can absorb that. We're also given that alpha naught's in P, so the product of alpha naught and something else, wherever it is in P again. So we can absorb that.
Okay. Yeah.
So it does in fact imply that alpha 1 beta naught is in P. And since P is prime, that implies either alpha 1 is in P or beta naught's in P. But of course we already knew, well, I guess we didn't already know that alpha 1 was in P, did we?
Do you have to like use induction?
Maybe. And so if we continue that, we'll eventually, well, but we already, if this continues, then I'd have all of these are in P. But again, that doesn't tell me anything about beta naught, because things in P multiplied by things outside go back into P. That doesn't give me information about beta naught. I'm clearly missing some aspect of the proof. So I'd encourage you guys to go back and look at page 309 on Dummett and Foote and find out what it is I'm missing today. I'm obviously missing something. Man, it seems so right to me when I wrote it out. God. Oh well, it is nevertheless true, despite my inability to convince you of the final and somewhat important point to the proof, because of course if we don't know that's in P squared, I don't get the contradiction. Sadness. Because I don't think I mean, some of these things I've written down, he never wrote down. So I can't really tell. Like, I don't think he ever wrote this.
Yeah, he never wrote out
No.
the specific coefficient.
Right, he never actually wrote the coefficients for the A of x and B of x. He just, yeah. All right, moving along. So, proposition 13, or rather 33. So skipping ahead a bit, this would be, bearing the lead here. So that, the proof is great, but what I really wanted to point out was its application. And so this example is where it's at. So take any field you like, adjoin an element T, all right? Then if you look at, this is polynomials, right, over the field F extended by T, right? And then we can show that x to the n minus T, if this is f of x, this is irreducible over f adjoin T, since, let's see here. So what do we got? What do we need to use Eisenstein? Well, since the can't remember. Oh, come on. Where'd it go? Since the ideal generated by T, right, is prime ideal. So if you look at it, if we have a product of elements is in the ideal generated by T, right, that means that at least one or the other of them is in the ideal generated by T again. Because if you have a multiple of T, at best you have at worst you have a constant times something basically a monomial in T, right?
So in other words, you don't have a square root.
Yeah. So that's a prime ideal of T. And then what else can we say? Well, actually there's another way to look at that, though. I mean, so yeah, in terms of the direct, but there's an easier way to see that that's a prime ideal, as opposed to just thinking direct in terms of direct calculation and products of elements being in here. Also, look at the quotient. If we take f adjoin T mod T, what do we get? In that quotient space, all of the non-constant terms have been quotiented to 0. It's not hard to see up to isomorphism that this is f, which is, of course, an integral domain.
Does that get rid of the inverse T terms as well? I guess it's not.
Yeah. And so, yeah, fair enough. Rational functions in T So we can, again in that quotient, anything t to any power essentially behaves as 0. So every rational function will just collapse down to its leading coefficients upstairs and downstairs. All right, this plus this thing, right, is equal to
That cause division by 0.
well, I mean, we always have to be. I'm going to cause division by 0. I don't think so.
Like, what if I start with, what if I say like 1, or just, what if I just say t inverse mod?
Well, 1 over, 1 over t. 1 over t, I think, would be an element of this, I think. Why is a good question. Yeah. Yeah.
Not even in t, then you can multiply them and then you get 1 in the algebra.
All right, say again. If
If you have, primary, you have an algebra by t, so you can multiply with 1 over t and you get 1.
Are you saying the ideal generated by t is prime because it's
I'm not sure it's even prime because it's the whole field.
but is it
Because,
since it's generated by just one element, does that make it prime?
No, just because that any idea in a field is either 0 or the whole field. So I suspect
Well, but is at the joint t of
it's still a field. I think you just use the square bracket like
do you think I'm supposed to have a,
yeah, the polynomial.
this is supposed to be a square bracket?
What is this example? Is this, like,
Would that fix it?
I don't know, I seem to remember it being at the joint t.
If I do that,
So t will be irreducible.
yeah. Well, oh, in f adjoint t? Aye.
No, it's still a square bracket of t. And t will be primary here because t is irreducible. And we got a quotient. And
I mean, I think that's also true. I mean, certainly t is irreducible. So if we take a polynomial ring mod a ideal generated by a irreducible polynomial, we get a field. I don't know, guys. I feel like you guys are talking me out of something I shouldn't be talked out of. Unfortunately, I did not bring my book. This is the example. What I'm doing is I'm taking the example right after the. It's back on page 309. The example right after it. I changed his big X to a little x and his little x to a t, so that it will match the example I got to last time. Well, anyway, grief.
It field here because you have a field and you got a prime ideal in that. And any ideal in a field must be zero or a whole field. But
Right.
prime ideals must not be either zero or a whole field because it's a prime ideal. It's the definition. Basically. I mean, you're not define prime ideal to be the whole field, the whole ring. That's the first condition.
Right.
And it's not also zero because we have a theory.
The prime ideal is not the whole ring, and it's not zero because there's no constants in the ideal generated by T, for example. Then what?
So that field will is a prime ideal in your field.
Prime ideal. Oh, in this is not a field. This is a ring, is your point. Yeah. Does anybody have their book? This is very unexciting. It's example 5 on page 310. You are correct. It is. Yep. So I have managed to butcher everything by changing certain square brackets to parentheses. It's all my fault. Ay. Thank you. Yes. So this is so everything Kang was saying and you guys were telling me is right. That's good. So at least you have learned something. So the polynomials in the I guess you could say indeterminate T form a ring because F is a field and it's an integral domain from stuff we did last semester. And then we can look at polynomials over that. For example, x to the n minus t is such a polynomial. And that is irreducible over the polynomials over t because in the polynomials over t, the ideal generated by t is a prime ideal of that ring of polynomials because the quotient of this by this by this is, so you guys are right to call me out on that nonsense up there. Thank you. So then this is clear, both calculationally and for theory reasons, right? Because if we take a polynomial in t and we reduce mod t, then everything non-constant vanishes to zero. We're left with a constant term, hence the isomorphism. Or, as you pointed out, this is irreducible. So if we take a, irreducible generates a what kind of ideal? Maximal ideal. So when we quotient by a maximal ideal, a ring, we get a field. And it has to be this field because it's, well, anyway. All right. So can we apply Eisenstein then? When you look at this, what do we got? We only have a sub 1 equals to minus t, right? And that's an element of this, which is playing the role of p in Eisenstein's criteria, right? And what is, well, excuse me, is that a sub 1? Hold on a second. What is that? That's a sub 0. Thank you. See, the relation, the meaning of t and x here, I just flip-flopped, which is the primary confusion that you might suffer from. And I was trying to remove before class, but I still suffer from it slightly. And can we see that, and it's monic, right? Yay. There's nothing else to check in terms of their coefficients. Is a sub naught, and then we also need what? We need that a sub naught is not an element of p squared, right? But p squared here is in fact t squared, right? And yes, minus t is not an element of the ideal generated by t squared. Because the ideal generated by t squared is multiples of t squared over the underlying field f. And minus t is not in there. So yes, we have met the conditions of Eisenstein. And so this implies what? This implies that x to the n minus t is irreducible. In, let's say, in any field adjoining T. Although I think we need characteristic, do we need anything about characteristic? I don't think we even need the characteristic 2 caveat, do we? No, I don't think we do. So the application we wanted to do last time was if we look at the field of, order 2, F2, Z mod 2 for us last semester, in this adjoin, this thing has what?
Friday we were doing a join.
Yeah. But let's see here, x squared, anyway, x squared minus t would be in here, right? And x squared minus t is irreducible. Over F2, yeah, it's not that's a little bit different than this, right? But I think this goes back to the interplay between like integer factorizations and rational factorizations, kind of the extension of that discussion. Like suppose you had a reduction of it. Suppose x squared minus t had a reduction over the field adjoining T. Then that would mean that this is equal to something like a of x, b of x, for, a of x, b of x where? Right? And then what you could do is if you had that reduction, I think you could clear out the denominators, and it would imply a corresponding reduction in the polynomials over T with F2 coefficients.
Would that be?
So if you multiply by the, sort of the product of all the denominators in a of x and b of x in this given reduction, then that would give me some constant m times x squared minus t, which was equal to what? Which was equal to, a tilde of x times b tilde of x, where the a tilde of x and b tilde of x were in F2 polynomials over T.
Then what do we do with M? M is a polynomial. How do we get the reduction?
Is M a polynomial? M is a polynomial in T, though.
Yes, polynomial T.
It's non-zero, too. I'm not sure what to do next there, annoyingly. Gauss's lemma. All right, well, there's a problem for you guys to think about. How do we get from there to there? Well, this was not as productive as I'd hoped. So, moral of the story today. Be careful that this is not this. And ignoring the distinction between these things implicitly as you write notes for a class is unwise. That seems to be the source of my downfall today, yes. I don't remember where. Did you guys remember where he shows x squared minus t is irreducible over f2? I mean, that m is a non-zero. That's a non-zero polynomial in what? In t.
I mean, I would love to apply Gauss lemma.
Apply what?
Apply Gauss lemma. I think it works for more bigger, more general ring like PID or even UFD.
So the generalized Gauss's lemma for rings. Yeah.
So F2 is F2T is integral. I mean, principal ideal rings.
Uh-huh. Well, yeah, I mean, that field is the rational functions over t. That's the field of fractions here. I'm trying to get a contradiction that if there was a reduction, if there was a reduction over over the rational functions in t, that would imply a reduction over the polynomials in t, which we know doesn't exist because of Eisenstein's. Criteria. Yeah. Yeah? No?
I think that you have a polynomial of degree 2 in x.
Yeah.
And I mean, you take the polynomial in variable x naught t. So
Degree 2 in x, yeah.
yeah, so both two factors must be degree 1. So they must have a root in F2t.
So for this to be a genuine reduction, it has to be, this is something like m1 times x minus c1, m2 x minus c2, something like this. Of course I could, and where's the c1s and c, oh, and those are in,
So they are roots. Polynomial.
Yeah, but then you
yeah,
So
c1 and c2 are roots of the polynomial.
and C1 and C2 is F2t.
c1 and c2 are from f2t. Yeah.
So you got so if you substitute into m times x squared minus t, you got a relation of t. I mean, algebraic relation.
Like m is m1 times m2. I mean, of course we could. Well, I mean, we can of course rewrite that as m times x minus c1 times x minus c2, I think. And what's that tell me?
And you just substitute x equal to c1.
X equal to c1. And what's that tell me?
And you got the right hand side is 0, the left hand side is an element of F2t.
So that forces c1 squared to be minus t to be equal to 0, right? Oh, here's the contradiction, guys. So if you assume, it's good, it's just calculation. If there is a reduction, then there has to be, if there's a non-trivial reduction, well, how do we know that these are linear?
because they're producing degree 2. They're producing
Oh, right,
degree 2 polynomial in x.
Right, I'm sorry, again, I'm getting confused with the interplay between the role of the rational versus the polynomial as it relates to the coefficients versus the polynomials in x. But you're right, for this to be a genuine reduction, these have to be first order in x, which means that there exists m1 and m2 such that this happens, But when you multiply that out, the leading coefficient has to be m, comparing these polynomials. Leading coefficient has to be the same, which means then the roots, if they did exist, would have to be C1 and C2 like so. Plugging in either one of them, for example, C1, on the left-hand side gives me that m, a non-zero scalar by construction, because it's multiplying out the denominators which are by necessity non-zero in the original expansion, times C1 squared minus t has to be 0. But that forces this to be 0 because that's non-zero. And this being 0 is tantamount to saying that C1 is root t, which is no allowed because root t is not in f adjoin t. So there you go. A reduction over the field would imply a reduction over the polynomials, which is a no-go because of Eisenstein's criteria. Yay! We have rescued this lecture modulo the giant gaping hole in the proof of Eisenstein's back here, which again not too. I would wager a careful reading of Dummett and Foote will fill in that gap, if I'm any judge of things. Yeah. So we may yet get to cyclotomic polynomials by Friday. Seems it's, well, anyway, if I play my cards right Wednesday, maybe I can actually, I would really like to beat a Galois theory by Friday. So, although that is not, that's a day ahead of my schedule, which would be a good thing. So, yeah. All right, well, I guess I'm done.
Okay, so we